And now in this lecture, we answer two questions. In the first question, we find out the area of this trapezoid ABCD. In the second question, we find out the area of this quadrilateral ABCD using two different methods. So we start with the first question. In the drawing, we have trapezoid ABCD. Side DA of trapezoid ABCD equals to 41 units in its length. Side CB also equals to 41 units in its length. Side AB equals to 50 units in its length. Again, our task is to find out the area of this trapezoid ABCD. So first of all, what is a trapezoid? A trapezoid is a quadrilateral with one pair of parallel sides. Again, trapezoid is a quadrilateral with one pair of parallel sides. Quadrilateral ABCD. In quadrilateral ABCD, side DC is parallel to side AB, therefore quadrilateral ABCD is a trapezoid. The two parallel bases, DC and AB, the two parallel sides DC and AB are defined as the bases of this trapezoid ABCD. If we define the length of base DC as A and the length of base AB as B, then the area of this trapezoid ABCD equals to the sum of its two parallel bases, exactly A plus B, times the height edge over 2. The height edge must create 90 degrees with the two parallel bases. Because again, the area of this trapezoid ABCD equals to the sum of its two parallel bases. In this case, it is A plus B times the height edge over 2. So first of all, we define the relevant points to this question with letters. We define, before that, inside trapezoid ABCD we have this circle, or this circle is inscribed by trapezoid ABCD. Or trapezoid ABCD blocks this circle. Again, our task is to find out the area of this trapezoid ABCD. So first of all, we define the relevant points of this question with letters. We define the point of tendency of tangent DC. If this circle, this point is point E. Likewise, we define the point of tendency of tangent CB with this circle, this point is point E. We define the point of tendency of tangent DA with this circle, this point is point F. And finally, we define the point of tendency of tangent AB with this circle, this point is point H. So here we can implement rule 2. I'll put quickly on rule 2. According to rule 2, the lengths of two tangents from a common external point to a circle are equal. So in the drawing we have a circle. This is the common external point P. From this common external point P, we have two tangents to this circle, tangent PA and tangent PB. And according to this rule 2, they are equal to each other. That is to say, PA equals to PB. So we can implement rule 2 in our drawing. Why? Because in our drawing, if we focus on this common external point D, from this common external point B, point D, we have two tangents to this circle, tangent DF and tangent DE. And according to rule 2, they are equal to each other. That is to say, DF equals to DE. So if we define the length of tangent DE as A, then the length of tangent DF must be also equal to A, because they are equal to each other according to rule 2. Likewise, we focus on this common external point C. On this common external point C, we have two tangents to this circle, tangent CE and tangent. Actually, we have 2 times the letter E, so I'll change the letter E to G. So, from the common external point C, we have two tangents to this circle, tangent CE and tangent CG. And according to rule 2, they are equal to each other. That is to say, CE equals to CG. So if we define the length of tangent CE as B, then the length of tangent CG must be also equal to B because they are equal to each other according to rule 2. Likewise, we focus on this common standpoint, point A. From the common standpoint, point A, we have two tangents to this circle, tangent AF and tangent AH, and according to rule 2, they are equal to each other. That is to say, AF equals to AH. So if we define the length of tangent AF as C, then the length of tangent AH must be also equal to C because they are equal to each other according to rule 2. And finally, we focus on this common standpoint, point B. From this common standpoint, point B, we have two tangents to this circle, tangent BG and tangent BH. And according to rule 2, they are equal to each other. That is to say, BG equals to BH. So if we define the length of tangent BG as D, then the length of tangent BH must be also equal to D because they are equal to each other according to rule 2. What is the length of side DA plus the opposite side CB in trapezoid ABCD? Again, what is the length of side DA plus side CB? DA plus CB in total equals to A plus B plus C plus D. So it is known. If we found out that A DA plus CB DA plus CB equals to A plus C, A plus B plus C plus D. What is the length of side DC plus the opposite side AB? DC plus AB in total equals to A plus B plus C plus D. So DA plus CB equals to A plus B plus C plus D, and DC plus AB also equals to A plus B plus C plus D. And because of the fact that those two expressions are both equal to A plus B plus C plus D, it means that they are equal to each other. This is to say DA plus CB equals to DC plus AB. So at the moment we found out that DA plus CB equals to DC plus AB. DA equals to 41 units in its length. Plus CB. CB also equals to 41 units in its length. And it is equals to DC. DC is the missing side, so leave it as it is. So it is DC plus AB. AB equals to 50 units in its length according to what is given as the question. So in total we found out that 41 plus 41 equals to DC plus 50. 41 plus 41 is 82 equals to DC plus 50. Here we subtract 50 from the equation. And again that the missing side DC is equal to 82 times 50 is 32. So the missing side DC equals to 32 units in its length. This is the missing side DC. equal to 32 units in its length. In the next step, we will do a construction, that is to say, from point C, we will do a perpendicular on AB. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point C and AB. This point is point J. In the next step, we will do another construction. That is to say, from point D, we will do perpendicular on AB. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point D and AB. This point is point N. ABCD is a trapezoid. In trapezoid ABCD, we have one pair of parallel sides, that is to say, side DC is parallel to the opposite side AB. Those two angles, they're both defined as one-sided interior angles, and are located between the parallel lines DC and AB. Therefore, according to Rule 17, the sum of two one-sided interior angles that are located between parallel lines is equal to 180 degrees. So if we go Rule 17, according to Rule 17, the sum of one-sided interior angles that are located between two parallel lines is equal to 180 degrees. In the drawing, we have line A that is parallel to line B. Then line C cuts the two parallel lines A and B at those 2 points. We also have those two angles alpha and beta that are defined as one-sided interior angles, and are located between the parallel lines A and B. Therefore, according to this rule, Rule 17, the sum of those two one-sided interior angles is equal to 180 degrees. That is to say, alpha plus beta equals to 180 degrees. So I can actually implement Rule 17 in our drawing. Because in our drawing, we have those two one-sided interior angles that are located between the parallel lines DC and AB. Therefore, the sum of those two one-sided interior angles must be equal to 180 degrees according to Rule 17. This is a right angle. That is to say, it is equal to 90 degrees in size, plus this vicinal angle, that is actually angle DCJ. In total, the sum of those two one-sided interior angles must be equal to 180 degrees according to Rule 17. Again, 90 degrees plus the missing angle DCJ, in total it must be equal to 180 degrees according to Rule 17. Here we subtract 90 degrees from this equation, and finally we get that the missing angle DCJ is equal to 180 degrees minus 90 degrees is 90 degrees. So the missing angle DCJ equals to 90 degrees in size according to Rule 17. This is the missing angle DCJ that is equal to 90 degrees in its size. Those two angles are both defined as one-sided interior angles, and they are located between the same parallel lines DC and AB. And therefore, according to Rule 17, the sum of those two one-sided interior angles must be equal to 180 degrees. This is a right angle. plus this missing angle, that is actually angle CDN. In total, the sum of those two one-sided intervals must be equal to 180 degrees according to rule 17. So repeat again, we should find out that 90 degrees plus the missing angle CDN, in total they must be equal to 180 degrees according to rule 17. Here we subtract 90 degrees from this equation, and finally get that the missing angle CDN is equal to 180 degrees minus 90 degrees, that is 90 degrees. So actually, this is the missing angle CDN, that is equal to 90 degrees in its size. So in quadrilateral DCJN, this is quadrilateral DCJN, we have 4 right angles, 1, 2, 3, 4. And therefore, according to rule 5, quadrilateral DCJN is a rectangle. Write it down, because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle DCJN, side DC must be equal to the opposite side JN, but DC is 32, therefore the opposite side JN must be also equal to 32 units in its length. Likewise, according to the same rule, in the same rectangle DCJN, side DN must be equal to the opposite side CJ. So those two sides are equal to each other. We'll focus on those two right angles. This is the right angle CJB and this is the right angle DNA. We'll prove that those two right angles can go into each other according to side rule. So why those two right angles can go into each other? First of all, those two sides are equal to each other according to the rule that the opposite sides of a rectangle are equal to each other. In addition, those two sides, they are both equal to 41 units in its length, in their lengths, according to what is given as the equation, therefore they are equal to each other. Those two sides are equal to each other. Why those two sides are equal to each other? I'll prove that those two sides are also equal to each other. Actually copy those two right angles in a new pattern and prove that those two sides are equal to each other. That is to say, side AN equals to side JB and those two right angles. So actually, those are the two right angles that are going from the original drawing. This is the right angle DNA, this is the right angle CJB. Those two sides are both equal to 41, therefore they are equal to each other. So actually define the length of those two sides as y. Those two sides are equal to each other according to the rule that the opposite sides of a rectangle are equal to each other. So if the length of side DN is x, then the length of side CJ must be also equal to x because they are equal to each other. What is the length of AN? We implement the Pythagoras theorem in order to find out the length of AN. This right angle DNA, according to the Pythagoras theorem, in any right angle, the square of their products equals to the sum of the squares of the perpendiculars. In the right angle DNA, it means that y square equals to x square plus an square. Again, y square equals to x square plus an square. Here we subtract x square from this equation and find out that an square equals to y square minus x square. Here we took a root out of this equation and found out that the length of the missing side an is equal to the square root of y square minus x square. Repeated on the same process of this right angle CJB. Actually, we implemented the Pythagoras theorem with this right angle CJB. According to the Pythagoras theorem, with this right angle CJB, y square equals to x square plus ab square. Y square equals to x square plus jb square. Here we subtracted x square from this equation and found out that jb square equals to y square minus x square. Here we took a root out of this equation and found out that the length of the missing side JB is equal to the square root of 1 square minus x square, exactly like side AN that is also equal to the square root of x square minus x square. And because of the fact that those two sides, they are both equal to the square root of y square minus x square, it means that they are equal to each other. That is to say, AN equals to JB. So if we found out in those two triangles, those two sides are both equal to y, therefore they are equal to each other. In addition, those two sides are both equal to x, therefore they are equal to each other. And finally, side AN equals to side JB. So if we found out that all the three sides of this right triangle DNA corresponding equal to all those three sides of this right triangle CJB, and therefore those two right triangles can go into each other according to side rule. And again, if we found out that, so I write it down, if we found out that those two right triangles can go into each other according to side rule. Right triangle DNA can point to the right triangle CJB according to side rule. We have already found out that side AN equals to side JB, and that is the main point here. We already found out that side AN equals to side JB. So side AN in the right triangle DNA is equal to side JB in the right triangle JCB. AN equals to JB. If we define the length of side AN as x, then the length of side JB must be also equal to x because they are equal to each other. The length of side AB is 50 units according to what is given as the question. From one side AB equals to 50 units, but from the other side AB consists of three line segments, AN, NJ, and JB. So from the other side AB also equals to x plus 32 plus x. So I write it down. From one side, line segment AB or side AB equals to 50, according to what is given as the question, but from the other side, it is also equals to x plus 32. X plus 32 is 2x plus 32. And from this equation, 50 equals to AB equals to 2x plus 32. We will derive that 50 equals to 2x plus 32. Here we'll subtract 32 from this equation, and finally we get that 50 minus 32 is 18, so 2x equals to 18. Here we'll divide this equation by 2, and finally we get that x equals to 18 over 2. 18 over 2 is 9, so x equals to 9 units in its length. Side JB equals to x and x equals to 9. That is to say, side JB equals to 9 units in its length. In the next step, I'll copy the right triangle CJB in a new page, and we will implement on this right triangle CJB the Pythagoras theorem. Here by PT is the progression for Pythagoras theorem. So actually, this is the right angle CJB that are going from the original domain. In this right angle CJB, CB squared, that is the square of the hypotenuse, equals to CJ squared plus JB squared. So I'll write it down. CB squared, that is the square of the hypotenuse, equals to CJ squared plus JB squared. CB is 41, therefore CB squared is 41 squared, that is 1681. And it is equal to CJ squared. CJ is the missing sign, so we leave it, so it is CJ squared plus JB squared. JB is 9, therefore JB squared is 9 squared, that is 81. So in total we should find out that 1681 equals to CJ squared plus 81. Here we will subtract 81 from this equation, and we get that 1681 minus 81 is 1600 equals to CJ squared. Here we will take a root out of this equation, and finally we get that the missing sign CJ is equal to the square root of 1600, that is 40. So CJ equals to 40 units in its length. This is the missing side CJ, that is equals to 40 units in its length. CJ, it is actually the height of trapezoid ABCD. Why CJ is the height? Because it creates 90 degrees with the two parallel bases. Our task is to find out the area of this trapezoid ABCD. So what is the area of trapezoid ABCD? According to the formula that I presented to you in the beginning of the lecture, the area of trapezoid ABCD must be equal to the sum of its two parallel sides. In this case it is CD plus AB times the height, that is CJ, over 2. But again, if you found out that the area of this trapezoid ABCD, that is the area that we're looking for in this question, total it is equal to the sum of its two parallel bases, that is actually CD plus AB, times the height CJ over 2. CD is 32 plus AB. AB is 50 times CJ. We already found out that CJ is 40 over 2. So in total we found out that the area of this trapezoid ABCD equals to 32 plus 50 times 40 over 2. 32 plus 50 is 82, and 40 over 2 is 20. So in total, the area of trapezoid ABCD equals to 82 times 20. 82 times 20 is 1640 square units in size. So she found out that the area of trapezoid ABCD, that is the area that we're looking for in this question, is equal to 1640 square units in its size. And that is the answer to the first question. Repeat again, I should found out that the area that we're looking for in this question, that is the area of this trapezoid ABCD, is equal to 1640 square units in its size. So we finish with the first question. In the next step, I will present to you the second question, and we'll solve the second question of this lecture by using two different methods. Our task in the second question of this lecture is to find out the area of this quadrilateral ABCD. So in the domain we have quadrilateral ABCD. This is side AB of quadrilateral ABCD. That is equals to 10 units in its length. This is side DC. This is equals to 25 units in its length. This is angle ABC. This is a right angle. This is angle ADC. This is also a right angle. This is angle BCD. This is equals to 45 degrees in its size. Again, our task is to find out the area of this quadrilateral ABCD. So first of all, we will do a construction. That is to say, from point B, we will draw perpendicular on DC. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point B in DC. This point is point N. In the next step, we will do another construction. That is to say, from point A, we will draw perpendicular on BN. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point A and BN. This point is point M. By doing this construction, we will quadrilateral AM and D. In quadrilateral AM and D, we have 1, 2, 3 rectangles. The sum of 3 rectangles is 270 degrees. So 270 degrees plus the size of this 4 facing angle, in total it must be equal to 360 degrees. According to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this 4 facing angle must be equal to 90 degrees in its size. So inside quadrilateral AB, AM, and D, we have 4 angles, and therefore quadrilateral AM and D is a rectangle. We define the length of side AM as A. That is to say, side AM equals to A units in itself according to our definition. We know that the opposite sides of a rectangle are equal to each other. So in rectangle AM and D, side AM must be equal to the opposite side ND. But AM is A, therefore the opposite side ND must be also equal to A units in its length. In the next step, we will focus on this right angle, triangle B and C. On the right angle B and C, this angle equals to 90 degrees, this angle equals to 45 degrees, and therefore this third missing angle must be equal to 45 degrees in its size, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. 45 degrees plus 45 degrees is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees. That is the sum of the angles in any triangle. We have the rule that states that in front of equal angles in the triangle, there are equal sides. So we focus on the right triangle B and C. On the right triangle B and C, in front of those two equal angles, we have those two sides that must be also equal to each other in their lengths. But what is the length of side NC? NC equals to DC minus DN. So if you know, if you found out that the length of side NC is equals to DC minus DN. So NC in total equals to DC. DC is 25 minus DN. DN is 8. So in total, if you found out that the length of side NC is 25 minus 8. NC equals to 25 minus A units in its length. Return on the right triangle B and C. On the right triangle B and C, in front of those two equal angles, we have those two sides that must be also equal to each other and their lengths. but side NC equals to 25 minus A, therefore side BM must be also equal to 25 minus A units in its length. So this is side BM, side BN, this is side BN, this is equal to 25 minus A units in its length. We know that the big angle ABC equals to 90 degrees in its side according to what is given as the question. So angle ABC plus this angle NBC, in total is 90 degrees plus 45 degrees. This is the size of the missing angle ABM. Again, the missing angle ABM equals to the big angle ABC minus the smaller angle NBC. This is the size of this angle ABM. So angle ABM equals to angle ABC, this is 90 degrees, minus angle NBC, this is 45 degrees. 90 degrees plus 45 degrees is 45 degrees. So this angle BM is equal to 45 degrees in its size. In the small right angle ABM, this angle equals to 45 degrees, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 45 degrees in its size, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. We continue to focus on the small right angle ABM. On the small right angle ABM, in front of those two equal angles, with those two sides, it must be also equal to each other and their lengths. But side AM equals to A, therefore side BM must be also equal to A units in its length. What is the length of this missing 97 MN? From the drawing it is very easy to see that MN in total equals to BN minus BM. So I don't know. Then the length of side MN is equal to BN minus BM. So MN in total equals to BN is 25 minus A, minus BM is A. So in total, MN equals to 25 minus A is 25 minus 2A. So actually, this is the missing 97 MN that is equals to 25 minus 2A units in its length. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle AMND, side AMN must be equal to the opposite side AD. But AMN is 25 minus 2A, therefore the opposite side AD must be also equal to 25 minus 2A units in its length. So AD equals to 25 minus 2A units. Quadrilateral A, B, and D is a trapezoid. Why quadrilateral A, B, and D is a trapezoid? First of all, we know that in rectangle A, M, and D, the opposite sides are parallel to each other. That is to say, side MN is parallel to the opposite side AD. BN is a straight line because of the fact that angle BMN equals to 180 degrees in its size, and we know that any angle that is equal to 180 degrees in its size, it is defined as a straight line. So BN is a straight line, but MN is part of the straight line BN. Again, MN is part of the straight line BN, and it is parallel to the opposite side AD. If a part of the straight line is parallel to another straight line, then the straight line itself BN must be also parallel to AD. So BN is parallel to AD, so in quadrilateral A, B, and D, side BN is parallel to the opposite side AD, and therefore quadrilateral A, B, and D is a trapezoid. So the drawing should handle this quadrilateral A, B, and D is a trapezoid because it has one pair of parallel sides. What is the area of trapezoid A, B, and D? Actually, the area of trapezoid A, B, and D is equal to the sum of its two parallel bases, that is actually BN plus AD, times the height AM over 2. Why the height is AM? Because it creates 90 degrees with the two parallel bases. But again, we should find out that the area of trapezoid A, B, and D equals to the sum of its two parallel bases, that is actually BN plus AD, times the height AM over 2. BN is 25 minus A plus AD. AD is 25 minus 2A times AM. AM is A over 2. So in total we should find out that the area of this trapezoid A, B, and D equals to 25 minus A plus 25 minus 2A times A over 2. 25 plus 25 is 50, and minus A minus 2A is minus 3A. So if I found out that 25 plus 25 is 50, and minus A minus 2A is minus 3A, times A over 2. So in total, if you found out that the area of trapezoid A, B, and D equals to 50 minus 3A times A over 2. Here we'll open the brackets of this expression and get that 50 times A is 50A, minus 3A times A is minus 3A squared over 2. So in total, if you found out that the area of trapezoid A, B, and D is equal to 50A minus 3A squared over 2. In the next step, we will implement the Pythagoras theorem on this small right triangle ABM. So I copy the small right triangle ABM in an equation. We will implement on it the Pythagoras theorem. Here by PT is the abbreviation for Pythagoras theorem. So actually this is the right triangle ABM, this is the coming from the original door. In this right triangle ABM, according to the Pythagoras theorem, BA squared, that is the square of the hypotenuse, equals to BM squared plus MA squared. So write it down. BA squared, that is the square of the hypotenuse, equals to BM squared plus AM squared. Plus AM squared. BA is 10, therefore BA squared is 10 squared, that is 100. And it is equals to BM squared. BM is 8, therefore BM squared is 8 squared. Plus AM squared. AM is 8, therefore AM squared is 8 squared. So in total we should find out that 100 equals to A squared plus A squared. A squared plus A squared is 2A squared. So we should find out that 100 equals to 2A squared, or 2A squared equals to 100. Our task is to find out the area of this quadrangle ABCD. So what is the area of quadrangle ABCD? From the drawing it is very easy to say that the area of quadrangle ABCD in total equals to the area of trapezoid A, B and D plus the area of this right triangle B and C. And again, we should find out that the area of this quadrangle AB and D, the area of this trapezoid ABCD, the area of this quadrangle ABCD, that is the area that we are looking for in this question. Total is equal to the area of trapezoid AB and D plus the area of the right triangle B and C. We have already found out that the area of trapezoid AB and D equals to 50A minus 3A squared over 2. But again, we already found out that the area of trapezoid AB and D equals to 50A minus 3A squared over 2. Plus the area of the right triangle B and C. What is the area of the right triangle B and C? The area of the right triangle B and C equals to the base of the triangle that is NC times the height that is NB over 2. So in total, the area of quadrangle ABCD is equal to the area of trapezoid A, B and D, that is 50A minus 3A squared over 2, plus the area of the right triangle B and C, that is the base NC times the height NB over 2. So the area of quadrangle ABCD in total is equal to 50A minus 3A squared over 2 plus the area of this right triangle B and C, that is the base NC, that is 25 minus A times NB, that is also 25 minus A, 25 minus A times 25 minus A is 25 minus A squared divided by 2. So in total, if you found out that the area of quadrilateral ABCD equals to 58 minus 3a squared plus 25 minus a squared over 2. So it is equal to 58 minus 3a squared plus 25 minus a squared. 25 minus a squared equals to 25 squared, it is 625, plus a squared minus 2 times 25 times 8, that is minus 50a over 2. 58 minus 50a is 0. So because of those two expressions, we left only with 625 minus 3a squared plus a squared is minus 2a squared over 2. So in total, we should find out that the area of quadrilateral ABCD equals to 625 minus 2a squared over 2. But 2a squared equals to 100. So we can substitute 2a squared in this expression by 100. We do it now, we get that the area of quadrilateral ABCD equals to 625 minus 2a squared. Minus 2a squared is 100 over 2. So in total, the area of quadrilateral ABCD equals to 625 minus 100 is 525 over 2. 525 over 2 is 262.5 square units in size. That is the answer to the second question. According to the first method, I repeat again, we actually found out that the area of this quadrilateral ABCD, that is the area that we are looking for in the second question, is equal to 262.5 square units in size. So we finish with the first method. In the next step, I present to you how to find out the area of this quadrilateral ABCD according to the second method. In the second method, we will do a construction, that is to say, we will extend side DA and side CB of this quadrilateral ABCD by a straight line until they touch each other. And we will define the touching point of the extended side DA with the extended side CB. This point is point M. By doing this construction, we get that the big right triangle MDC. The big right triangle MDC, this angle equals to 90 degrees. This angle equals to 45 degrees, and therefore this third missing angle must be equal to 45 degrees in its size, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. We will continue to focus on the big right triangle MDC. We have the rule that in front of equal angles in the triangle, there are equal sides. So repeat again, in front of equal angles in the triangle, there are equal sides. So in the right triangle MDC, in front of those two equal angles, we have those two sides that are equal to each other. But side DC equals to 25 units in its length, therefore side DM must be also equal to 25 units in its length. MC is the hypotenuse of the big right triangle MDC, MC is an hypotenuse, it is absolutely a straight line. So if you focus on the left side of the straight line MC at point B, here the sum of the angles must be equal to 180 degrees according to Rule 3. Rule 3 says that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the left side of the straight line MC at point B? We have this angle that is a right angle plus this missing angle. In total the sum of those two angles must be equal to 180 degrees according to Rule 3. Therefore this missing angle must be equal to 90 degrees in its size. So in the small right triangle A and B, this angle equals to 90 degrees, this angle equals to 45 degrees, and therefore this third missing angle must be equal to 45 degrees in its size according to the rule that the sum of the angles in any triangle is equal to 180 degrees. We will continue to focus on the small right triangle A and B. On the small right triangle A and B, in front of those two equal angles, we have those two sides that must be also equal to each other and their lengths. But side AB equals to 10 units, therefore side AB must be also equal to 10 units in its length. Our task is to find out the area of this quadrilateral ABCD. So what is the area of quadrilateral ABCD? From the drawing, it is very easy to see that the area of this quadrilateral ABCD, in total it is equal to the area of the big right triangle MDC minus the area of this small right triangle MBA. And again, we should find out that the area of this quadrilateral ABCD, that is the area that we are looking for in this question, in total it must be equal to the area of the big right triangle MDC minus the area of the small right triangle MBA. The area of the big right triangle MDC, it is equal to the base DC times the height MD over 2. Again, the area of this big right triangle MDC is equal to the base DC times the height MD over 2. Minus the area of the right triangle ABM or MBA. What is the area of this right triangle MBA? Is equal to the base of this triangle MBA, this is AB, times the height, that is BM, over 2. Repeat again, the area of this one right triangle MBA, in total it is equal to the base AB times the height BM over 2. DC is 25 times MD. MD is also 25 over 2. So the area of this big right triangle MDC, in total it is equal to 25 square over 2 minus the area of the small right triangle MBA. The area of this small right triangle MBA is equal to AB, that is 10, times BM, that is also 10, divided by 2. So in total we should find out that the area of quadrilateral ABCD, in total it is equal to 25 squared minus 10 squared over 2. 25 squared is 625 minus 10 squared, that is 100, over 2. 625 minus 100 is 525 over 2. 525 over 2 is 262.5 square units in its size. So in both methods, you can find out that the area of this quadrangle ABCD, that is the area that we are looking for this question, is equal to 262.5 square units in its size. So we finish with the second method of the second question. In the next step, I will start with the next one. We'll start with the first question, of course. In the first question, our task was to find out the area of this trapezoid ABCD. So what is a trapezoid? A trapezoid is a quadrilateral with one pair of parallel sides. This is quadrilateral ABCD. In quadrilateral ABCD, side DC is parallel to the opposite side AB, and therefore quadrilateral ABCD is a trapezoid. The two parallel bases, the two parallel sides, that is to say DC and AB, are defined as the bases of this trapezoid ABCD. If we define the length of the base DC as A and the length of the base AB is B, then the area of this trapezoid ABCD must be equal to the sum of its two parallel bases, that is actually A plus B, times the height edge over 2. The height edge must create 90 degrees with the two parallel bases. And again, a trapezoid is a quadrilateral with one pair of parallel sides, and the area of the trapezoid equals to the sum of its two parallel bases times the height over 2. So first of all, actually, in the drawing we have trapezoid ABCD that blocks this circle, or this circle is inscribed by trapezoid ABCD. So first of all, we define the relevant points of this question with letters. We define the point of tendency of tangent DC with this circle. This point is point E. Likewise, we define the point of tendency of tangent DA with this circle. This point is point F. We define the point of tendency of tangent CB with this circle. This point is point G. And finally, we define the point of tendency of tangent AB with this circle. This point is point H. In the next step, we implemented rule 2 in our drawing. Repeat quickly on rule 2. According to rule 2, the lengths of two tangents from a common external point to a circle are equal. So in the drawing we have a circle. This is the common external point, point P. From this common external point, point P, we have two tangents to this circle, tangent PA and tangent PB. And according to this rule 2, they are equal to each other. That is to say, PA equals to PB. So we can actually implement rule 2 in our drawing. Because in our drawing, if you focus on this common external point, point D, from this common external point, point D, we have two tangents to this circle, tangent DE and tangent DF. And according to rule 2, they are equal to each other. That is to say, DE equals to DF. So if we define the length of tangent DE as A, then the length of tangent DF must be also equal to A, because they are equal to each other according to rule 2. Likewise, we focus on this common external point, point C. From this common external point, point C, we have two tangents to this circle, tangent CE and tangent CG, and according to rule 2, they are equal to each other. That is to say, CE equals to CG. So if we define the length of tangent CE as B, then the length of tangent CG must be also equal to B, because they are equal to each other according to rule 2. Likewise, we focus on this common external point, point A. From this common external point, point A, we have two tangents to this circle, tangent AH and tangent AF. And according to rule 2, they are equal to each other. That is to say, AH equals to AF. So if we define the length of tangent AH as C, then the length of tangent AF must be also equal to C, because they are equal to each other according to rule 2. And finally, we focus on this common external point, point B. From this common external point, point B, we have two tangents to this circle, tangent BJ and tangent BG. And according to rule 2, they are equal to each other. That is to say, BH equals to BG. So if we define the length of tangent BH as D, then the The left from tangent BG must be also equal to D because they are equal to each other according to rule 2. What is the value of side CB plus side DA? From the drawing, it is very easy to see that CB plus DA in total equals to A plus B plus C plus D. Read again. DA plus CB equals to A plus B plus C plus D. What is the value of side DC plus the opposite side AB? DC plus AB in total equals to A plus B plus C plus D. And again, we found out that DC plus AB also equals to A plus B plus C plus D. And because of the fact that those two expressions are both equal to A plus B plus C plus D, it means that they are equal to each other. That is to say, DA plus CB equals to CB to DC plus AB. Again, DA plus CB equals to DC plus AB. DA is 41, CB is also 41, DC is the missing side, and AB is 50. 41 plus 41 is 82, equals to DC plus 50. Here we subtract 50 from this equation, and finally found out that DC equals to 82 minus 50 is 32. So DC, the missing side DC, this is the missing side DC, is equals to 42 units in its length. In the next step, we did a construction, that is to say, from point D we do perpendicular on AB. So this angle equals to 90 degrees and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point D and AB. This point is point N. Likewise, we did another construction. From point C we do perpendicular on AB. So this angle equals to 90 degrees and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point C and AB. This point is point J. Trapezoid ABCD. In trapezoid ABCD, we have one pair of parallel sides. That is to say, side DC is parallel to the opposite side AB. Those two angles are defined as one-sided interangles and are located between the parallel lines DC and AB, and according to Rule 17, the sum of those two one-sided interangles is equal to 180 degrees. But this is a right angle. That is to say, 90 degrees plus the size of this missing angle, that is angle DCJ, in total must be equal to 180 degrees according to Rule 17. And again, 90 degrees plus the size of the missing angle DCJ, in total must be equal to 180 degrees according to Rule 17. Here we subtract 90 degrees from this equation and find out that the missing angle DCJ equals to 180 degrees minus 90 degrees, that is 90 degrees. So this is the missing angle DCJ, that is equal to 90 degrees in its size. Likewise, the sum of those two one-sided interangles that are located between the parallel lines DC and AB is equal to 180 degrees according to Rule 17. This is a right angle plus the missing angle CDN, in total must be equal to 180 degrees according to Rule 17. Okay, again, so we found out that 90 degrees plus the missing angle CDN, in total must be equal to 180 degrees according to Rule 17. Here we subtract 90 degrees from the equation, and finally found out that the missing angle CDN equals to 180 degrees minus 90 degrees is 90 degrees. Okay, this is the missing angle CDN. This is the missing angle CDN. That is equals to 90 degrees in its size. So in quadrilateral DCJN, we have 4 right angles, 1, 2, 3, 4, and the whole quadrilateral DCJN is a right angle. But we know that the opposite sides of a right angle are equal to each other. So in right angle DCJN, side DC must be equal to the opposite side JN. But DC is 32, therefore the opposite side JN must be also equal to 32 units in its length. Likewise, according to the sum rule, in the sum right angle DCJN, side DN must be equal to the opposite side CJ. So in those two right triangles, this is the right angle, this is the right angle DNA, and this is the right angle CJB. Those two right angles can go into each other according to side rule. That is to say, those two sides are equal to each other according to the rule that the opposite sides of a rectangle are equal to each other. Likewise, those two sides, they are both equal to 41 units, and therefore they are equal to each other. And finally, those two sides are also equal to each other. Actually, copy those two rectangles in a new page, and I prove that those two sides are equal to each other. That is to say, side AN in the rectangle DNA is equal to side JB in the rectangle CJB. Those are the two rectangles that are coming from the original domain. The hypotenuses of those two rectangles are both equal to 41 units in their lengths. So actually, we find the hypotenuses of those two rectangles is y instead of 41 units. Those two sides are also equal to each other according to the rule that the opposite sides of a rectangle are equal to each other. So if we define the length of side DN as x, then the length of side CJ must be also equal to x because they are equal to each other. And finally we have those two sides. So why those two sides are equal to each other? Actually implemented the Pythagoras theorem on this rectangle DNA. According to the Pythagoras theorem, in any rectangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. In the rectangle DNA, it means that y squared equals to x squared plus an squared. Y squared equals to x squared plus an squared. Here we subtracted x squared from this equation and finally found out that y squared minus x squared equals to an squared. Here we took a root out of this equation and finally found out that the missing side an equals to the square root of y squared minus x squared. This is the missing side an. This is equal to the square root of y squared minus x squared. Repeated on the same process on this rectangle CJB. In the rectangle CJB, according to the Pythagoras theorem, y squared equals to x squared plus jb squared. Again, y squared equals to x squared plus jb squared. Here we subtracted x squared from this equation and finally found out that jb squared equals to y squared minus x squared. Here we took root out of this equation and finally found out that the missing side jb equals to the square root of y squared minus x squared. Exactly like side an that is also equals to the square root of y squared minus x squared. And because of the fact that those two sides, that is to say side an and side jb, they are both equal to the square root of y squared minus x squared, it means that they are equal to each other. That is to say, side an equals to side jb. Okay. We found out that side an equals to side jb. So actually, the rectangle DNA is converted to the rectangle CJB according to side rule. And we already proved that side AN equals to side JB. So if we define the length of side AN as x, then the length of side JB must be also equal to x because they are equal to each other. Side AB, or trapezoid ABCD, equals to 50 units in its length according to what is given in the question from one side. But from the other side, side AB consists of three line segments, AN and J and JB. So from the other side, side AB in total equals to x plus 32 plus x. We can again found out that from one side, side AB equals to 50, but from the other side, side AB equals to x plus x plus 32. X plus x is 2x, so in this side of the equation we have 2x plus 32. This is equals to AB and AB equals to 50. From this equation, 50 equals to AB equals to 2x plus 32. We will derive that 50 equals to 2x plus 32. Here we subtracted 32 from this equation. And we finally found out that 2x equals to 50 minus 32 is 18. 2x equals to 18. Here we divided this equation by 2 and finally found out that x equals to 18 over 2 is 9. So actually, this is the missing side JB that is equals to x, and x equals to 9, that is to say JB equals to 9 units in its length. In the next step, I copied the right triangle CJB in the new page and implemented the Pythagoras theorem on this right triangle CJB. The hypotenuse CB equals to 41 units, JB equals to 9, and CJ is the missing side. So here, this is the right triangle CJB that I copied from the original drawing. This right triangle CJB, according to the Pythagoras theorem, CB squared, that is the square of the hypotenuse, equals to CJ squared plus JB squared. The hypotenuse CB equals to 41, therefore CB squared equals to 41 squared, that is 1681, and it is equals to CJ squared. CJ is the missing side, so we have to it is CJ squared plus JB squared. JB is 9, therefore JB squared is 9 squared, that is 81. So in total we should find that 1681 equals to CJ squared plus 81. Here we subtracted 81 from this equation, and we found out that CJ squared equals to 1681 minus 81 is 1600. So CJ squared equals to 1600. Here we took out all of this equation, and we found out that the missing side CJ equals to the square root of 1600, that is 40. So this is the missing side CJ, that is equals to 40 units in its length. CJ is also the height of trapezoid ABCD. Why CJ is the height? Because it rests 90 degrees with the two parallel bases DC and AB. So CJ is the height of trapezoid ABCD. Our test is to find out the area of this trapezoid ABCD. So what is the area of trapezoid ABCD? According to the formula that I presented to you in the beginning of the lecture, the area of trapezoid ABCD must be equal to the sum of its two parallel bases, that is to say DC plus AB, times the height CJ over 2. And again, the area of this trapezoid ABCD, that is the area that we are looking for in this question, is equal to the sum of its two parallel bases, is roughly CD plus AB, times the height CJ over 2. CD is 32, AB is 50, CJ is 40 over 2. 32 plus 50 is 82, and 40 over 2 is 20. So in total, we should find that the area of trapezoid ABCD equals to 82 plus 20. 82 plus 20, 82 times 20. 82 times 20 is 1640. So in total, we should find out that the area of this trapezoid ABCD is equal to 1640 square units in its size. We finish with the first question. In the next step, I presented to you the second question, and we solved the second question by using two different methods. Our task in the second question is to find out the area of this quadrilateral ABCD. So the drawing again quadrilateral ABCD, this is side AB, that is equals to 10 units in its length. This is side DC, that is equals to 25 units in its length. This is angle ABC, that is a right angle. This is angle ADC, that is also a right angle. This is angle BCD, that is equal to 45 degrees in its size. Again, our task is to find out the area of this quadrilateral ABCD. So in the first step, we did the construction, that is to say from point B, we draw perpendicular on DC. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point B in DC, this point is point N. In the next step, we did another construction, that is to say from point A, we do perpendicular on BN. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point A and BN, this point is point M. By doing those constructions, we get the quadrilateral AM and D. Inside quadrilateral AM and D, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this fourth facing angle, in total they must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this fourth facing angle must be equal to 90 degrees in its size. So inside quadrilateral AM and D, we have 4 right angles, and therefore quadrilateral AM and D is a left angle. We define the length of side AM as A. We know that the opposite sides of a left angle are equal to each other. So a left angle AM and D, side AM must be equal to the opposite side ND, but AM is A, therefore the opposite side ND must be also equal to 1 unit in its length. In the next step, we focus on this right triangle BNC. In the right triangle BNC, this angle equals to 90 degrees. this angle equals to 45 degrees, and therefore this fourth missing angle, this fourth missing angle, must be equal to 45 degrees in its size, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. What is the length of this missing line segment NC? NC equals to DC minus DN. Again, NC equals to DC minus DN. So NC equals to DC. DC is 25 minus DN. DN is 8. So in total, NC equals to 25 minus the units in its length. So in the entire B and C, in front of those two equal angles, we have those two sides that must be also equal to each other, according to the rule that in front of equal angles in the triangle, there are equal sides. But this side equals to 25 minus 8, therefore side BN must be also equal to 25 minus the units in its length. This is the angle ABC. This is the right angle, this is equal to 90 degrees in its size. So the big angle ABC minus the small angle NBC must be equal to the missing angle ABM. Therefore the missing angle ABM must be equal to angle ABC that is 90 degrees minus angle NBC that is 45 degrees. 90 degrees minus 45 degrees is 45 degrees. So this is angle ABM that is equal to 45 degrees in its size. So in the small right angle ABM, this angle equals to 45 degrees. This angle equals to 90 degrees, and therefore this first missing angle must be equal to 45 degrees in its size, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. So in the right triangle ABM, in front of those two equal angles, we have those two sides that must be also equal to each other in their lengths. But side AM equals to 8, therefore side BM must be also equal to A units in its length. What is the length of this missing line segment MN? MN equals to BN minus BM. And again, MN equals to BN minus BM. So MN in total equals to BN, that is 25 minus A, minus BM, that is A. So in total, MN equals to 25 minus A minus A, that is 25 minus 2A. So MN equals to 25 minus 2A units in its length. So in left angle AMND, side MN equals to the opposite side AD. But MN is 25 minus 2A, therefore the opposite side AD must be also equal to 25 minus 2A units in its length. This is quadrilateral AB and D. Quadrilateral AB and D is a trapezoid. Why? Because it has one pair of parallel sides. Side BN is parallel to side AD. Why side BN is parallel to side AD? First of all, we know that the opposite sides of a rectangle are parallel to each other. So in left angle AM and D, side MN must be parallel to the opposite side AD. But BMC, angle BMC equals to 180 degrees in its side, and we know that any angle that is equal to 180 degrees in its side, it is defined as a straight line. Therefore, BN is a straight line, and MN, that is part of the straight line BN, is parallel to AD. But if a part of the straight line is parallel to another straight line, then the straight line itself, BN, must be also parallel to AD. So BN is parallel to AD. In quadrilateral ABCD, AB and D, side BN is parallel to the opposite side AD, and therefore quadrilateral AB and D is a trapezoid. This is exactly the definition of a trapezoid. A trapezoid is a quadrilateral with one pair of parallel sides. The quadrilateral AB and D, side BN is parallel to side AD, therefore quadrilateral AB and D is a trapezoid. And again, we should find out that quadrilateral AB and D is a trapezoid. So what is the area of this trapezoid AB and D? The area of trapezoid AB and D equals to the sum of its two parallel sides. The sum of its two parallel sides, that is actually BN plus AD times the height AM over 2. Repeat again, the area of trapezoid AB and D equals to the sum of its two parallel sides, that is actually BN plus AD times the height AM over 2. BN is 25 minus A plus AD. AD is 25 minus 2A times AM. AM is A over 2. And again, BN is 25 minus A plus AD, that is 25 minus 2A times AM, that is A over 2. So in total, we should find out that the area of trapezoid AB and D equals to 25 minus A plus 25 minus 2A times A over 2. 25 plus 25 is 50. minus A minus 2A is minus 3A times A over 2. We open the brackets here and found out actually that 50 times A is 58, minus 3A times A is minus 3A squared over 2. So in total we found out that the area of this trapezoid A, B, and D is equal to 58 minus 3A squared over 2. In the next step, we implemented the Pythagoras theorem on this small triangle ABM. So I copied the right small triangle ABM and implemented the Pythagoras theorem on this small right triangle ABM. So actually, this is the small right triangle ABM that according to the original drawing, this small right triangle ABM, BA squared, that is the square of the hypotenuse, equals to BM squared plus MA squared. BA is 10, therefore BA squared is 10 squared, that is 100, and it is equals to BM squared. BM is 8, therefore BM squared is A squared, plus MA squared. MA is 8, therefore MA squared is A squared. So in total, we found out that 100 equals to A squared plus A squared, that is 2A squared. So 100 equals to 2A squared, or 2A squared equals to 100. Our task is to find out the area of this quadrangle ABCD. So what is the area of this quadrangle ABCD? From the drawing, it is very easy to see that the area of quadrangle ABCD in total is equals to the area of trapezoid A, B, and D, plus the area of this right triangle B and C. Triangle B and C. So again, the area of quadrangle ABCD in total equals to the area of trapezoid A, B, and D, plus the area of the right triangle B and C. We already found out that the area of trapezoid A, B, and D equals to 58 minus 3A squared over 2, plus the area of the right triangle B and C. This is the right triangle B and C. What is the area of this right triangle B and C? The area of the right triangle B and C equals to the base NC times the height LB over 2. And again, the area of the right triangle B and C total equals to the base NC times the height LB over 2. So, the area of quadrangle ABCD equals to 58 minus 3A squared over 2. We have NC. NC is NC is 25 minus 8 times BN. BN is also 25 minus 8. So NC is 25 minus 8 and NB is also 25 minus 8. That is to say NC times BN is 25 minus 8 squared divided by 2. So in total, the area of quadrangle ABCD equals to 58 minus 3A squared plus 25 minus 8 squared. 25 minus 8 squared equals to 25 squared, that is 625, plus A squared, minus 2 times 25 times 8, that is minus 58 over 2. 58 minus 58 is 0, minus 3A squared plus A squared is minus 2A squared over 2. In total, we should found out that the area of quadrangle ABCD is equals to 625 minus 2A squared over 2. But we have already found out that 2A squared equals to 100. So we can substitute 2A squared in this expression by 100. We did it, and we found out that the area of quadrangle ABCD equals to 625 minus 2A squared. Minus 2A squared is 100 over 2. So in total, the area of quadrangle ABCD equals to 625 minus 100 over 2. 625 minus 100 is 525 over 2. 525 over 2 is 262.5 square units in its size. So she found out that the area of this quadrangle ABCD equals to 262.5 square units in its size. We finished with the first method. In the next step, I presented to you how to find out the area of this quadrangle ABCD according to the second method. In the second method, we did a construction. That is to say, we extended side DA and side CB of this quadrangle ABCD by a straight line until they touch each other at this point. We define their touching point, this point M. By doing this construction, we get here the right big triangle MDC. On the right big triangle MDC, this angle equals to 90 degrees, this angle equals to 45 degrees, and therefore this third missing angle must be equal to 45 degrees in its size. According to the rule that the sum of the angles in any triangle is equal to 180 degrees. And we'll continue to focus on the right triangle MDC, on the right big triangle MDC. we have the rule that in front of equal angles in the triangle, they are equal size. So in the right triangle MDC, in front of those two equal angles, we have those two sides that must be also equal to each other and their lengths. But side DC is 25, therefore side MD must be also equal to 25 units in its length. MC is the hypotenuse of the big right triangle MDC, so MC is an hypotenuse, it is absolutely a straight line. So if you focus on the left side of the straight line MC at point B, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 says that the sum of the angles on one side of the straight line is equal to 180 degrees. So which angles we have the straight line MC at point B? We have this angle that is right angle plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its side. So, in the small right triangle MBA, this angle equals to 90 degrees. This angle equals to 45 degrees, and therefore this third missing angle must be equal to 45 degrees in its size according to the rule that the sum of the angles in any triangle is equal to 180 degrees. We'll continue to focus on the small right triangle MBA. And the small right triangle MBA, in front of those two equal angles, we have those two sides that must be also equal to each other with their lengths. But side AB is 10, therefore side MB must be also equal to 10 units in its length. Our task is to find out the area of this quadrilateral ABCD. So what is the area of quadrilateral ABCD? From the drawing it is very easy to see that the area of this quadrilateral ABCD equals to the area of the big right triangle MDC minus the area of this small right triangle MBA. Okay, again, the area of this quadrilateral ABCD must be equal to the area of the big right triangle MDC minus the area of the small right triangle MBA. The area of the big right triangle MDC equals to the base DC times DM times the height DM over 2. Okay, again, the area of the big right triangle MDC equals to the base DC times the height MD over 2. Minus the area of this small right triangle MBA. The area of this small right triangle MBA equals to the base AB times the height BM over 2. Repeat again, the area of the right small triangle MBA equals to the base AB times the height BM over 2. DC is 25, MD is also 25. DC is 25, MD is also 25. So in total, the area of the big right triangle DMC equals to 25 square over 2. AB is 10, MB is also 10. Again, AB is 10 and MB is also 10, so the area of this small right triangle MBA is equal to 10 square over 2. 25 square is 625, minus 10 square is 100 over 2. 625 minus 100 is 525 over 2. 525 over 2 is 262.5 square units in size. So in both methods, we actually found out that the area that we are looking for in this question, that is the area of this quadrilateral ABCD, is equal to 262.5 square units in size. Okay, thank you very much.